Right. Along with me going over the answers, I am also going to discuss a couple of points, which are viscosity v temperature and this idea of yield point and strength and then stiffness as well. I'm going to do it by answering a couple of questions, and I'm going to throw those points in as well. You can add the notes in your writing books a while ago over this. Okay. Right. Question one. What you've got is a wing moving to the left. So the air is going to flow over the wing this way. It's not going to flow that way. For those of you who have drawn your incoming arrows this way, I've got that wrong. So what you've got is laminar flow up to point A. You need to draw at least two of these lines. Otherwise, you won't pick up that mark. The second mark is for showing turbulent flow after point A. So you draw these eddies past point A or pointing in different directions, similar to the way I've drawn them. And that picks you up 2 marks. Question 2, multiple choice here. I want to kind of just go over the idea of what brittle and malleable are. A stress strain graph for malleable will maybe follow Hooke's law up to a point, and then after beyond the limit of proportionality, you get plastic deformation. This here is where the material starts to get longer and longer, i.e. the strain increases, the extension increases for a small amount of stress. And that's a malleable material. A brittle material does not show any plastic deformation region. It gets to a point, breaks, done. That is a graph that signifies that the material is brittle. So, say a state which can undergo a large plastic deformation without cracking, it will be a malleable. With no plastic deformation, that would be brittle. Okay, right. Question 3. Now, there's a couple of ways to answer this question. I'm going to answer it the way I've shown here. So the first part, it says a spring extends 9 centimeters with a force of 6 newtons. So I've shown you here. You can work out with that information the force constant for that spring. Now I've left it in centimeters, so my force constant is going to be newtons per centimeter. My answers here are in centimeters, so there's no need to convert it to meters. Now that might be handy. Let's look to the next part. Another identical spring is joined end to end with this spring, and a force of 4 newtons is applied. So end to end is a spring there connected to the other end. There's another spring there. Okay, and 4 newtons of force is acting there. These springs are in series, and the overall force constant for springs in series. So the overall force constant for springs in series, 2 springs, so it'll be 1 over K1 plus 1 over K2. Now we know that they're identical springs with a force constant of 0.66 reoccurring, and that I've put in there, and what I get is 1 over K is equal to 3, so K is equal to 1 over 3 Newton per centimeter. This is the overall force constant for both of the springs together. So that K now is the overall force constant of 2 of those connected together. Individually, they still have that force constant. Now, why have I done that? Now I can use F equals Kx again here. Here I've got the force of 4 newtons. Okay, and now rather than use K as 0.66, I need the overall force constant for this system. So I've worked that out to be a third. So it'll be 4 over a third, and that's 12 centimeters. Okay, now that's one way of doing it. If you found another way of doing it, that's absolutely fine. Right. So here is my additional part, additional teaching. I think I've missed this out, how viscosity changes with temperature. Okay, so how viscosity of a material changes with temperature. So you've got a ball bearing that is dropped through a liquid and its terminal velocity is measured. The experiment is repeated at different temperatures. So we didn't do that. We didn't change your fairy liquid to a different temperature or your glycerol to a different temperature. We just kept that the same. Okay, but viscosity is a function of temperature. Your equation had no mention of temperature when we looked at terminal velocity. However, viscosity does change with temperature. You can add that into your notes. How does it differ from gas to a liquid? It does. The reasoning behind this goes beyond what we need to know in year 12, but I will go over it. So for a gas, as the temperature increases, the viscosity also increases. Okay, so let's get through into our heads what's the difference between viscosity and density. Density is the mass over the volume. Okay, so if I increase the temperature of a gas and I keep the volume the same, the number of particles doesn't change, so the mass does not change. Okay, so the density is equal to mass over volume. So if I increase the increase the temperature of a volume of gas in, let's say, this box, and the size of this box does not change, so the volume stays fixed, and the number of particles is not escaping, so the mass stays fixed. So what happens is the density of that gas does not change. However, by increasing the temperature of that, all those particles in that box, all those gas particles, actually does increase the kinetic energy of those particles. Now, those particles are going to be colliding with the object as that object moves through. So more energetic collisions, you're going to get increase in friction resistance, and as a result, increase in viscosity. Okay, so with gases, we have to look at something called the kinetic theory of gases, which you'll look at in year 13. But if you think about it, if the temperature of a gas increases, the average speed of the particles increases. Therefore, they collide with the object that is passing through that gas more energetically, therefore increasing the drag. So, i.e., increasing the viscosity, the frictional force on the actual object. Okay. But with a liquid is the opposite. So as the temperature increases, the viscosity decreases. So a classic example of this is if you've got something like oil that goes into your car. When it's inside the container, it is quite thick, and you pour it into your car engine. Once the engine starts running, and the engine's hot, the oil goes through that. And when you're replacing the oil, often it's very, very thin. And increase in temperature of oil makes it a very runny. So when it's cold, it's like honey. Whereas when it's hot, it's like water. Okay. So as the temperature increases, the viscosity decreases. Now, in terms of an explanation to that, now we can't use the same explanation as gases, okay? But what we've got is by increasing the temperature, what happens is that the particles move freely between the layers, and as a result, and the molecular structure changes so that the particles can slide over one another easily, and as a result, the texture changes of that actual liquid. Okay, so the viscosity changes as a result. So with temperature, with liquid, as the temperature increases, the viscosity decreases. So here in this question, we have a ball bearing drops through a liquid and the terminal velocity is mentioned. So if we decrease, it's a liquid, remember, so we're looking at this statement here. So as a temperature decreases, the viscosity is going to increase, it's going to do the opposite. So these two go hand in hand. It could be A as well. Or it could be D as well, because that follows the viscosity temperature relationship. However, if the viscosity is greater, that means that you're going to get more resistance to motion. So what you're going to get is a terminal velocity will be much lower. So here is what we're looking at. Okay, so we've got an answer of the lower the viscosity, the greater, the lower the temperature, the greater and the viscosity, and the slower the terminal velocity. Here, for part D, you would have had a higher terminal velocity for a lower viscosity. Okay. Question 5, what we've got is, we've got 4 materials, A, B, C, D. Which materials have the greatest strength? Now, the material that reaches the highest stress, we will assume that point at the end of each line is the breaking point. The highest stress before it breaks, A. Okay, so greatest strength, the largest stress defines the strength. So A has the largest stress compared to all of the other materials, and